Welcome learners. In today's lecture, we are going to talk about application of Gauss's law, and the application will focus on finding the value of electric flux density, which is d of s, a vector quantity, for various charge distributions. Our goal will be to find the charge distribution on a symmetric Gaussian surface represented by g of s, so that our mathematical calculations become as simple as possible. So the idea is that we want to find, or we want to use, the Gauss's law to find the electric flux density d of s. This is in the same principle as we utilized Coulomb's law to find the electric field intensity in the previous discussions. So for the electric field intensity, our focus was on finding its value for the charge distributed for a point charge. Then we had a line charge distribution represented by rho L. Then we had a surface charge distribution represented by rho S. And finally, we had a volume charge distribution. In case of electric flux density d of S, we'll always focus on symmetric distributions, which means we'll find the value of electric flux density for point charge. We will look into the infinite line charge, and we'll also look into the distribution in a coaxial cable. So our intention is to only look into these conditions because they offer symmetry with the Gaussian surface. So it means if I have a point charge, the electric field is symmetric around it. If I take a line charge, the electric field or the Gaussian surface that will be encompassing this electric field will be symmetric. Similarly, we'll have a coaxial cable with two conductors, inner and outer, that will form the Gaussian symmetry. So now let us see what the Gaussian equation basically was. So Gauss's law represents the total charge enclosed that depends upon the charges enclosed in a surface with its electric flux density d of s and a dot product of its small area d of s. So this is our main Gauss's equation, and it always relates to the electric flux that is passing through the charge, but we'll focus on this boxed equation. So in order to find the electric flux density d of s, in order to find the electric flux density, which is represented as d of s, we need to have few conditions in mind. Remember, this s means that the flux is leaving the surface. So the flux is leaving that surface. Okay, so the two conditions that we have to keep in mind. The first is we should know what kind of charge distribution we are dealing with, which means whether we have a point charge, we have a line charge, we have a surface charge, or whatever it is, what kind of distribution it is on the object. The second point is that we need to choose the correct Gaussian surface. We need to choose the correct Gaussian surface. By correct Gaussian surface, it means that we should have a closed surface such that the charge is evenly distributing its energy. And in order to have this closed surface, we further need to abide by two more conditions, and that is that our electric flux density d of s should be everywhere either normal to the charge or tangential. So if it is normal, it means that the dot product of electric flux density and the small area d of s in our equation number 1 will not be equal to 0, because the dot product is basically if you have a vector A with a vector B and you take its dot product, so it is absolute of A, absolute of B, cos of the angle between them. So if they are having no angle among them, they are going to have a certain value, that is cos of 0. But if it is a tangential element, or the d of x, or electric flux that is flowing, is tangential, then the dot product between the two elements will be equal to 0, as there will be a certain angle, probably a perpendicular angle between them. So this is the subcondition A that we have to know, and the subcondition B is that once the electric flux density is not equal to 0, or we can say this part of the equation, so d dot d of s, when both the elements are not equal to 0, we are going to assume that d of s is having a constant value everywhere. So this simplifies our equation in terms of analysis. This means that equation number 1 for the Gauss's law is now simplified as the charge equals to d of s, which is now a coefficient. It will be outside the closed surface integral, and we will be only left by integrating the element, which is a small portion, that is d of s. So equation number 2 is now our simplified representation of the Gauss's law around any closed or symmetric surface. So now once we know this, let us now find the value of electric flux density for a point charge. So the idea is such: we want to find what is the value of electric flux density due to a point charge which is located at the origin. So we are taking the point charge at the origin, and there is a certain radial distance in the form of value of r, and in the 3D representation we have just selected a small portion with regards to the axis provided for this coordinate system. So the idea is we need to reach towards this equation of the electric flux density for a point charge distribution. So let us understand and apply the two conditions to reach towards this position. So we want to find the electric flux density, which is represented as d of s for the point charge. So what we can do is so if I make a point charge and represent it in the form of a 2D representation, so if this is a point charge, we enclose it by a symmetric Gaussian surface, and the charge is radiating in all the directions uniformly. So this is a 2D representation. Now what are the two conditions? The first is what kind of charge distribution is. So we know that this is a point charge, so the charge distribution is a point charge. And what kind of Gaussian symmetric structure we are selecting? We are selecting the spherical coordinate systems as a symmetric Gaussian surface. And obviously what should be the flow of direction of the electric flux? So the electric flux is always radially outward or normal to the Gaussian surface, which means that d of s could be any value over here. So we can select it, or we can make it more clearly as, if this is my charge q, I surround it with a spherical Gaussian surface. So this is my Gaussian surface. Now I select a point P over here, and the distance from the origin to this point is r, and if I extend it, I can go towards the electric flux density, which is always normal to the surface. So the portion here that I have selected is the small portion d of s, and obviously the unit vector will be normal, which is equal to a of r. So this is the visualization of the 3 points which we have selected, and now let us find the electric flux density equation. So we already know from the Gauss's law, or from equation number 2, which we have seen previously, that the charge enclosed is equal to the electric flux density, which is now a coefficient, and you have the surface integral of d of s. Now we know that the electric flux density will remain a constant, and this is a double integral. Since we are using spherical coordinate systems and the point P is selected along the radial component, so we know for the spherical coordinate system the 3 axis values are r, theta and phi. So we want to integrate for theta and phi for which the ranges are 0 to pi for theta and 0 to 2 pi for the phi angle, and the value of ds will be, this is the differential element when dealing with the spherical coordinate system. So the differential element for the spherical coordinate systems is d of r d theta, and you have r sine theta d of phi. Since we are just having a point along the radial axis, so d of r will not be part of this, thus d of s comes out to be, so d of s comes out to be r square sine theta d theta d phi. So we can replace d of s value over here as r square sine theta d of theta d of phi. Now once we have the values of the small surface area d of s where the differential elements, we can integrate it. So we can first integrate it with regards to the phi value. So we will have 0 to pi r square sine theta d theta, and I can integrate from 0 to 2 pi d of phi. Now this portion comes out to be pi with the limits of 0 to 2 pi, and this is equal to 2 pi. So now I'll take the 2 pi as a coefficient outside. So I will have d of s. This r square can be brought outside the integral, and I am now only left with 0 to pi sine theta d theta. So if I integrate this portion, it comes out to be minus cos of theta with the range from 0 to pi. This comes out to be minus cos of pi minus cos of 0. So it comes out to be minus 1 minus, and this comes out to cos of 0 is plus 1. So this comes out to be 2. Equation now comes out to be 4 pi d of s r square, and that is basically the value of the charge. Since I am interested in finding the electric flux density, so the value of electric flux density d of s on any closed surface is now equal to q divided by 4 pi r square. And if I want to make it a vector, I'll write it the unit vector with the unit of coulomb per meter square. So this is the electric flux density for a point charge as per the application of Gauss's law. And once we know the electric flux density, we can also find the electric field intensity, because the electric flux density and the electric field intensity are mathematically related as such. So electric field intensity then comes out to be q divided by 4 pi epsilon naught r square into a of r into volts per meter. So this is the equation of the electric field intensity, and we have seen this equation in the first lecture of this chapter, but now we have mathematically proven that electric flux density for a point charge is having this value, and similarly the electric field intensity for the point charge will be as such. Now let us come to the second application of Gauss's law, and that is the electric flux density due to a uniform line charge. So again we are taking a uniform line charge. In this scenario it is placed around the z-axis. This is the line charge having charges and a specific value of rho of L. So instead of taking the line from minus infinity to positive infinity, we have just restricted our length towards z equals to 0 to L. This will make our integration process easy. And now let us find what is the equation of the electric flux density due to this giant charge which is located along the z-axis. So let us understand it. What we want is, we have a line charge. So let me draw this again. This is our coordinate system. This is y-axis, x-axis and z-axis. We have a line charge along the z-axis. So again with the two conditions, the first is what kind of charge distribution we are having. So we are having an infinite line charge distribution. And what is the second point? What kind of a symmetric Gaussian surface it would be? So in this case it will be cylindrical surface, which means that our axes will be rho, phi and z. So I can enclose this in this cylindrical Gaussian surface. So the line is now enclosed. This is my Gaussian surface, and the line charge distribution will be represented as rho of L. So again, if I take a small portion of patch over here and see what is the effect, so from the line charge, the effect is represented as the radial distance rho of L, and if I extend this, it can be my ds A of n, where A of n is a normal vector, and that's the visualization or representation of my line charge in a symmetric Gaussian surface which is cylindrical in nature. And obviously the third point, we have already seen that the electric flux density is radially outward or normal to the surface, normal to the Gaussian surface. So these are the 3 points that we have taken. Now again, our equation will remain the same, that we start by using the Gauss's law equation, where we have a surface integral with electric flux density and the small surface d of s in vector form. We know that since d of s is a coefficient or a constant everywhere, it will be outside the integral, and thus we will be left with double integrals of d of s. So since this is radially outward, so this means that our integral will cover only phi and z axis. So we can say this is our phi ranging from 0 to 2 pi, and this is our z, which is from 0 to L, not from minus infinity to infinity, because we have given it a certain length of L. So now we need to find what is the value of d of s. So again, it's a differential element for the cylindrical coordinate system, and the differential elements for the cylindrical coordinate system is d of rho, rho d phi, and d of z. Since the analysis on the radial component, so d of rho will not be in this part, so the equation comes out to be d of s in double integral, this is phi, this is z, and d of s will have a value of rho d of phi d of z with the unit vector a of rho. So again, if we integrate this, so this is straightforward. D of s is the coefficient will stay out. We integrated with respect to phi, so I can first say that z is like this from 0 to L, then it will be rho d of z, and the integral will be for phi 0 to 2 pi d of phi. So again, if we integrate this portion, it comes out to be 2 of pi, and then we integrate z portion, so it will be L. So my value of the charge comes out to be d of s 2 pi rho of L. This is the charge which I am getting. Again, we need electric flux density, so it comes out to be the ratio of charge divided by 2 pi rho of L, and in order to make it a vector, we'll write the unit vector a rho. So this is the electric flux density for an infinite line charge, and we can further simplify it by writing it in the form of, so Q by L can be represented as line charge distribution divided by 2 pi of rho into A of rho. So this is the second form representation of the electric flux density. And again, so how did I reach to this? We know that the line charge distribution is the ratio of charges per unit length. So I've just taken this portion and represented it as rho of L. So this becomes my second equation. So this is in coulombs per meter square. Again, the electric field intensity can also be extracted, because we know the relationship between electric field intensity and electric flux density. So here the electric field intensity comes out to be Q divided by 2 pi epsilon into rho into A of rho in the units of volt per meter. So this is the electric field intensity, and this is the electric flux density, which is acting as an application of the Gauss's law, keeping in mind that we are using the symmetric Gauss's law. So now let us look at an example and understand how we can utilize these line charges and surface charges in finding the electric flux density. So in this question, we have been given a point charge of 0.25 microcoulomb located at r is equal to 0, and then we have been given multiple uniform surface charge densities located at 2 millicoulomb per meter square for r is equal to 1 centimeter and minus 0.6 milli into r is equal to 1.8 centimeter. We need to find the electric flux density for part A, B, and C, and then in part D we need to figure out what is the value of the uniform surface charge density located at r is equal to 3 that causes electric flux density to become 0 at r is equal to 3.5. So let us start by first visualizing this problem. So we start by first, so we know that we have a point charge. Let's say this is my point charge and I call this Q1, having a value of 0.25 microcoulomb, and it is at r is equal to 0 centimeter. So r is equal to 0 means that this sphere has no shape. Now the second thing, we know that we have uniform charge densities for r is equal to 1 and r is equal to 1.8. So let me draw half portion or a slice of a sphere. So this is at r is equal to 0. Let us say this is at r is equal to 1. So at r is equal to 1 centimeter, the surface charge distribution, let me call this rho S1, is equal to 2 millicoulomb per meter square. Then at r is equal to 1.8, so let me take this region. So this is r is equal to 1.8 centimeter. My surface charge density is minus 0.6 millicoulomb per meter square. Now I need to find or calculate the electric flux density at r is equal to 0.5. So I need to find r at 0.5 centimeter. So let us draw the 0.5. So obviously 0.5 centimeter is going to exist between 0 and 1. So I can say this is my r is equal to 0.5 centimeter, and I need to find what is the value of the electric flux density for this radius of sphere. So I can see that this is a spherical coordinate system because value of r is indicating as such. So in order to find the value of r, let me come over here. So this is the first part. So we know that for a point charge distribution, the electric flux density is equal to charge divided by 4 pi r square along the unit vector a of r. So we know that the charge is 0.25 microcoulomb, it means 10 raised to power minus 6 divided by 4 into 3.14. Now r square is basically, r is at 0.5 centimeters, so I can write it in meters. 0.5 into 10 raised to power minus 2 whole square, and then I have the unit vector a of r. So this is the expression that I am getting. So my answer comes out to be 795.77 a of r microcoulomb per meter square. So this is the electric flux density for the first part, and it is straightforward. So we can see that it is almost equal to the solution of the provided over here. So this is the answer, and again visualization gives us an idea what is happening. So what is happening is that the point charge at Q1 is basically radiating its energy, and once it reaches this portion, we need to find the value of D on this point. So the value of D is obviously going to be the combination of all these as an electric flux density. So we found the electric flux density for the first part. Now let us come to the second part and see what they are asking. So in the second part, the radius is now moved to 1.5 centimeters. So let us draw 1.5 centimeters. So let us say this will be my 1.5 centimeter. So let us say this is my 1.5 centimeter. Again, I need to find what is the value of electric flux density at this point in sphere, or at this radius of 1.5 centimeter. So for the second part, let me use this space. Again, the electric flux density equation will remain the same because the main source is a point charge. So it will be Q divided by 4 pi r square. So r will be replaced at 1.5 into 10 raised to power minus 2 whole square into a of r. So this is the expression that we are getting for the second part. But now we want to focus that what is the value of Q, or rather I should say what should be the Q total over here. Why? Because we want to find the electric flux density at this radius of 1.5 centimeter. So if you look over here, there are two sources that are applying the force. The one is the force coming from Q1 that has reached the previous D at a radius of 0.5, and the second is the force that is coming from surface charge distribution at r is equal to 1 centimeter. So I can say that there is a sheet of charge over here, and its effect is also going to be seen at the value of radius 1.5 centimeter along with the q1 point charge. So this means that we have to apply the principle of superposition to find the value of the total charge. That will be the sum of the first point charge, that is q1, and let me call this q2, which will be the surface charge. So this is my q2, which I need to find for this surface charge distribution. So now what can be q2? If I focus on this, so q2 is basically, we know that any surface charge distribution is represented as the charge per unit its shape. If it's a line, it will be length. If it's a surface, it is S. If it's a volume, it's an area. So in this case, it is a surface distribution. So I can say that the value of q2 comes out to be the surface charge distribution multiplication with an area. So the surface charge is 2 into 10 raised to power minus 3 multiplied with the surface charge of an area or the sheet. So this is a sphere, so I can immediately say it is 4 pi r square, where r in this case is 1 centimeter. So it is 2 into 10 raised to power minus 3, 4 pi 10 raised to power minus 2 whole square. So q2 comes out to be 2.5132 microcoulomb. So now once I have q2, I can figure out the value of qt. So qt is the total charge is q1 plus q2, and that is 0.25 microcoulomb plus 2.5132 microcoulomb, and the total charge for me comes out to be 2.763 microcoulomb. So this is q of t. Once I know q of t, I can just integrate it into the main equation for the electric flux density, and let me use this portion. So electric flux density for this complete values comes out to be 2.763 microcoulomb divided by 4 into 3.14 into 1.5 into 10 raised to power minus 2 whole square into A of r, and the final answer for me comes out to be 977 along the unit vector A of microcoulomb per meter square. So this is the electric flux density which we are getting for the second scenario, when the charge is lying at the radius of 1.5 centimeter, and we can confirm that the answer almost matches the same one. So this was the second part's solution. Now let us come to the third part, and in the third part use this one. So now in the third part, it is saying now the radius is at 2.5 centimeter. So 2.5 centimeter means that I need to draw the radius a bit far. Let's say this is radius of 2.5 centimeter, and I need to again find what is the electric flux density for this scenario. So again the principle remains the same, the equations remain the same. The idea is, so the equation for the electric flux density for the third part is the same as q divided by 4 pi r square into A of r. We know that q is what we need to find, but the r value is 4 pi. This time the radius is at 2.5 centimeter, so it is going to be 2.5 into 10 raised to power minus 2 whole square into A of r. Again for this scenario we need to find what is the total q. So what is the total q in this case? So let's go back to the visualization. So we need to find what is the electric flux density at this radius. So how many sources of energy are entering into this point? So we can see that the first source will come from q1, the second source will come from rho s1. So I can write it over here, or let's do, so the first source will come from q1 over here. Let us use the same lines. the second will come from this sheet. They will reach towards this point. So this is, both the effects are coming towards this point. Now we can see that at r is equal to 1.8 there is another sheet with the value or surface charge distribution of minus 0.6 meter. So again we have a sheet of charges over here, and the combined effect will be from this sheet and the remaining two charges, that is a point charge q1 and the q total that we previously found in part B. So this means that my qt is now going to, or let me call this qt bar, so just to differentiate. So qt bar is going to be the value of qt from the previous solution plus, let me call this position as q3 now. So this is the q3 that is coming due to the effect of this surface charge. So now this becomes q3. So I already know the value of qt, that is 2.763. So this is 2.763 microcoulomb, plus I need to find q3. So again it's going to be rho of s multiplied by the area. So rho of s in this case is minus 0.6 meter. So this is going to be 0.6 into 10 raised to power minus 3, and the value of rho for this sphere is 4 pi r square, because this is lying at r is equal to 1.8. So 1.8 into 10 raised to power minus 2 whole square. This comes out to be, this portion comes out to be minus 2.4429 microcoulomb. So now my qt bar comes out to be 2.763 microcoulomb minus 2.4492 microcoulomb, and it comes out to be 0.3203 microcoulomb. So I incorporate this q of t in this equation. So my electric flux density comes out to be, so the value is, the charge is going to remain as 0.25 and the remaining elements are as such. So the final answer comes out to be, if I write the equation, this is going to be qt bar divided by 4 pi r square into a of r. All the values are with us, so it is 40.8 a of r microcoulomb per meter square. So this is the electric flux density which I am getting, and let us confirm if this is the answer. And yes, indeed it is the answer that we are getting for the third part. So now let us come to the final part of the problem, and the final part is saying that you need to find the uniform surface charge density. So we need to find a rho of s in the final part D of the problem, when which is established at r is equal to 3 centimeter, that causes the electric flux density to become 0 at r is equal to 3.5. So then I need to find at r is equal to 3 centimeter, let us say this is r is equal to 3 centimeter, and another thing is r is equal to 3.5 centimeter. So I need to find the value of rho of s at r is equal to 3 centimeter, that causes the electric flux density to become 0 at r is equal to 3.5. Now this is an interesting problem. So now I need to find the rho of s that causes the electric flux at r is equal to 3 to come equal to 0. So if I look at rho of s, so let me write it as first. Now for the final part I need to find the rho s, let us say such that, and this is located at r is equal to 3 centimeter, and it causes d equals to 0 at r is equal to 3.5 centimeter. So this is what I need to find. Okay, so I know that the surface charge distribution is dependent upon charges per unit surface area. Now till now, if I look at my image, I know that whatever charges are, they are going to contribute by having a value of rho s over here. So it means that the total charge that I am getting is already known to me for the previous case. So the total charge which I found, this qt of dash, is basically the charge that is appearing till electric flux for r is equal to 2.5. In the previous example we have found the value of total charge. So this means I just need to incorporate this qt as qt bar. The value of this is 0.3203 microcoulomb and divided by the area of the sphere, which is 4 pi r square, and r square in this case is, I need to find it at r is equal to 3 centimeter to 3 into 10 raised to the power minus 2 whole square into a of r. So this should be my equation. But one thing to note here is that we are bound by the question that you need to find the surface charge distribution here at r is equal to 3 such that the electric flux density becomes equal to 0 on the radius 3.5. So in order to make this electric flux density equal to 0, I need to negate the total charge value. So this should be my negative charge value. So this means that the qt which I have and which I'm equating it to, let's say q of 4, let's say for this scenario it is now q of 4. So the Q4 that I am going to have is going to have a negative value of the total charge, hence that my positive charge and negative charge cancel each other out. In that case my electric flux becomes equal to 0. So that's why we have taken a negative sign for the total charge, and its value now comes out to be minus 28.3 microcoulomb per meter square. So this is the answer for the final part of the question, and let us confirm that indeed it is the answer over here. So this was the solution to the final part, and the thing to remember is that in order to get the electric flux density 0 at 3.5, we need to make sure that the charges are moving in the opposite direction. So the effect of positive and negative cancels out, and thus we get the value of rho of s over here as required. Now let us come to the last part of today's lecture, and that is the application on the coaxial cable. So how the electric flux density can be calculated if we have a coaxial cable, and why we selected a coaxial cable, because we want to understand the distribution of charges based on these symmetric Gaussian surfaces. So in order to understand this, we have an image of a coaxial cable. A coaxial cable basically has two inductors. One is the inner inductor, which is made of a conducting material. Then there is an air gap or any dielectric field over here, and then we have a bigger outer conductor that is surrounding the inner conductor. So again, for our analysis, we are restricting the length of this coaxial to be a specific length of L, and you can see that the Gaussian surface made over here is in the cylindrical form. So now let us find the electric flux density value or equation for the coaxial cable. So let us understand this. Now we have a coaxial cable, and we want to find the electric flux distribution or its value for this scenario. So a coaxial cable is basically a combination of two conductors. You can say one is an inner conductor, one is an outer conductor. We can have a better view of it. For example, if I make it as we have an inner conductor and we have an outer conductor. So the radius of inner conductor is, let's say, r equals to a, and radius of outer conductor is r equals to b, and we can basically take its view in terms of the Gaussian distribution as well. So this is my inner conductor surrounded by an outer conductor as such. So normally we assign this a value of rho of s inner, and we say this is rho of s outer, because we can see it's a sheet that has been wounded or wound together in a cylindrical form. So this means that we can start our analysis by by understanding the two conditions. So the first condition is, what kind of charge distribution should we begin with? So we know that any surface charge distribution can be represented, or a part or any part of a sheet. Let's say if this is my rho of s, I can have charges on this sheet. I can also represent this sheet by narrowing it down to a single line. We have seen this previously in the proof as well. So any sheet can be represented by a narrow line. So this means I'll begin my analysis for the coaxial cable by considering that although the inner conductor is having charges, but I'm going to assume that it is a line charge distribution. So I can say that my charge is an infinite line charge. And now what can be a symmetric Gaussian symmetry? So obviously it can be cylindrical. And the third point is that the electric flux density will always be normal or radially outward. So this means I can draw my Gaussian surface as such, or I'll use another color to have this idea clear. So my Gaussian surface will be a cylindrical one surrounding the inner conductor of the coaxial cable. So this is my Gaussian surface. I can have my Gaussian surface over here as well. Again, its radius will be rho. The Gaussian surface can be on this representation of the cable as well. So this is my Gaussian surface, and based on the conditions for finding the electric flux density, I took my charge to be an infinite line charge. My Gaussian surface is now cylindrical and ds is always normal to the axis. So now let us do the analysis and find the electric flux density equation. So the idea is I want to understand what is happening first between the charges appearing at the Gaussian surface and the charges available on the inner side of the conductor. This is what I want to know. So this is my equation number 1. So in order to understand this, let us see what is happening at the Gaussian surface. So since the inner conductor is considered as a line charge, let us first see what we know about the infinite line charge. So we know that the electric flux density for an infinite line charge is the ratio of charge, or let's write it first in the basic equation. It is basically line charge distribution divided by 2 pi of rho, and this is the unit vector A of rho. I can also represent this if I open the value of the line charge distribution as Q divided by rho of L into A of rho. So since I am interested in finding the charge distribution, so I can write this as the charge is equal to d 2 pi rho of L, and since I want to know what is happening at the Gaussian surface, so I can represent this as a Gaussian surface. Basically I want to know what is the value of charge at the Gaussian surface over here to verify the equation number 1. So this is the first thing which I got. Now let us see what is happening inside the inner conductor, or what are the charge distributions inside the inner conductor. So we know that the charge distribution or the inside of the conductor is basically dependent upon the surface charge distribution, which is of the inner conductor, and you multiply it with the total length of this cylinder, since we have taken the length to be L. So the surface area of a line is 2 pi RL. I can further write it as we select the inner value, and it is 2 pi, the value of radius for the inner cylinder is A of L. So this is my second equation. Now we use these two equations, or we equate, let's say, equation 2 and equation 3 as equation 1. So from equation 1 I can say, from equation 1, if I input the values for both the scenarios, it is going to be d q Gauss is equal to d 2 pi rho of L, and it is equal to rho s inner 2 pi A of L. So if we cancel out the values of the 2 pi and length, so electric flux density comes out to be the ratio of A divided by rho into rho s of inner. So this is the electric flux that is existing between what? It is existing between the inner conductor and the Gaussian surface. So this is the electric flux existing between the inner conductor and the symmetric Gaussian surface. Now what further can I do? I can use this equation. I can further simplify this equation. I can input the value of inner from equation number 3. So electric flux density can also be represented as A divided by rho Q of inner divided by 2 pi A of L. If I cancel L and L, this equation can also be written as rho of L divided by 2 pi rho, and to make it a vector I'll write A of rho. So this is a second representation in coulombs per meter square of the electric flux density. And if we can see closely, this equation is the same as that of the infinite line charge distribution. So you can find the electric flux density of a coaxial cable, that is the value or charges on the inner conductor, to that of the Gaussian surface, that comes out to be either of this form or it is the same as line charge distribution, because our basic analysis started by considering the inner conductor to be a line charge. So our analysis started as inner conductor is equal to an infinite line charge. So that is why we are getting the second value of the electric flux density to be in this form. So now once we have understood this, let us now understand what is the relationship between the inner conductor and outer conductor. So now till now what we have done is we have taken the inner conductor and we took the Gaussian surface. Let's say this is the Gaussian surface, or let me draw it with the different pen. So we have the inner conductor, we had the outer conductor, and till now we have basically found the electric flux density between the inner conductor and this Gaussian surface represented by the green color over here. So we found a value of D between these two. Now what is the relationship between the inner conductor and the outer conductor? We also want to find that out, because as per Coulomb's law, or as per Faraday's law, we know that the total flux passing is equal to the total charge, or we know that whatever is the charge inside, it is going to appear at the outer surface of the charge or the sphere with a negative charge. So this means that if we know what is, for example, if plus q was the charge on the inner conductor, we found that the same charge should exist on the inside of the Gaussian surface. And now if this charge is appearing at the Gaussian surface, then the outer conductor should have the same charge but with the negative sign. So let us see the relationship now. If you want to find the relationship between the outer sphere, let's say rho s outer, and the inner sphere, that is rho s inner. So we want to get a mathematical representation for the inner and outer. So we know if the charge is plus q on the inner side, the outer side should be the same charge with the negative value. So let's prove this to just. We know that q inner is rho s inner, and then you have a value of t 2 pi a of l because the radius is a, and q outer is rho s outer. So I'll put this in parenthesis, 2 pi b of l because the radius of the outer conductor was b. So once you do the comparison, so the value of the outer cylinder or the surface charges on the outer cylinder is the ratio of the radiuses with the value of the inner cylinder. So this is the expression which you can use to find the relationship between the inner and outer conductor. One important thing to realize is that we have seen this previously as well, that whenever we have two conductors, let's say this is an inner conductor and this is an outer conductor, the electric field and the electric flux density is only going to exist in between the inner and outer conductor. It is not going to exist inside or on the surface of charge of the conductors. So the E field and D field, this is an important note for you, that the E field and D field are only going to exist in between the conductors, and they are not going to exist inside the conductor or on the surface of the conductor. So this is an important point to remember. So that's how we find the electric flux density equation for a coaxial cable. Either you can use this equation or you can use the second equation. Similarly, if you want to find the surface charge for the inner conductor, or you want to find the surface charge of the outer conductor, we can utilize these equations. Let us look at an example and further understand how we can find these things. Let us look at an example and further understand how we can find this. Let's say we have a question to solve. So let's say we have been given the following data. So the data is that we have a cylinder or a coaxial cable with the inner and outer cylinders. The total length is 50 meters, and this is the Gaussian surface, which is cylindrical obviously. So the radius of the inner surface, is 1 millimeter. The radius of the outer surface is 4 millimeters. So the radius of the inner surface is A and radius of the outer surface is B. Okay, and we have been given that the charge on the inner conductor is plus 30 nanocoulomb, and we need to find what is the value of the surface charge distribution on the inner conductor, the surface charge distribution on the outer conductor, what is the value of electric flux and electric field intensity for this scenario. So let us solve this. So immediately we know by Faraday's principle that whatever charge is inside is going to be the same charge on the outer conductor with a negative sign. This means that the outer conductor will have a value of minus 30 nanocoulombs. Okay, this is good. Now we want to find what is the value of the surface charge on the inner conductor. So that is the ratio of the Q inner divided by the area 2 pi a of L. So this is the same equation which we have seen over here. This is equation number 3 which we are utilizing. So the value of Q inner is 30 nanocoulomb. It is 10 raised to power minus 9 divided by 2 into pi, which is 3.14. The area is 1 into 10 raised to power minus 3 and length is 50 meter. So the answer comes out to be 9.55 microcoulomb per meter square. So this is the surface charge distribution of the inner conductor. Now if I want to find the surface charge distribution of the outer conductor, I can use this equation, that is the ratio of minus A by B and whatever is the answer of the surface charge of the inner conductor. So it comes out to be minus 1 divided by 4 in millimeter, and the value of inner charge is 9.55 microcoulombs. So the answer comes out to be minus 2.39 microcoulomb per meter square. Or you can also use this equation as well for the outer, since the inner is having the value of A by B, the outer can also be used. So this is, you can use the ratio of charge divided by the 2 pi BL, but this equation is also acceptable. So now once we know this equation, how to find the electric flux density and electric field. So we know that the electric flux density is going to exist between the charges, and since this is a line charge distribution, so I can use the equation Q inner divided by 2 pi rho of L around A of rho. So the value comes out to be, the charge is 30 into 10 raised to power minus 9 divided by 2 into 3.14. Rho is basically the value of this is so this is the Gaussian surface. So since we are talking about inner, so this is going to be inner rho. So this is 9.55, and then you have a length of 50 into 10 raised to power minus 2 in the meter. So finally we get the value of D as 9.55. okay, so now we don't know what is the inner value, because the question is not given as the value of the rho, so we can just keep it as rho, because we are not finding the surface charge, rather we are finding the electric flux density on the Gaussian surface. So that's why the answer comes out to be 9.55 by rho along A of rho coulomb per meter square. And then if order to find electric field intensity, you just take the value of D and divide it by epsilon naught, and it comes out to be 1079 divided by rho volts per meter. So this is the solution of this problem. Again, the value of rho was not given to us whether we want to use the value of the inner conductor or outer conductor, since rho is the Gaussian surface. So if you remember, if we have the radius A, this is the radius B, so this is A, this is B, so the rho was the radius for the Gaussian surface. So this is my Gaussian surface. So in order, because we don't have the value of the rho for the Gaussian surface, it is an imaginary, so in the answer we keep this value as rho. And this is the solution of this problem, and this is related to finding the values for the coaxial cable distribution or charge distribution in a symmetric Gaussian surface based on coaxial cable. And that concludes our lecture.